Imagine you have a robot arm, and you give it a command to pick up an object in front of it. Sometimes the arm gracefully reaches its destination, but other times, no matter how hard it tries, it just cannot get there. This isn't a malfunction. It is often a fundamental limitation within the robot's design or the task itself. So, what causes this seemingly simple task to become an impossible mission for our mechanical friend? An inverse kinematics problem becomes unsolvable when the desired target position and orientation, also known as the target pose, falls outside the robot manipulator's physical capabilities or accessible workspace. In simpler terms, the robot simply cannot physically reach the requested point in space with the specified hand orientation. This means there is no combination of joint angles that can achieve the required end-effector pose. The core reason for these unsolvable scenarios lies in the inherent mechanical constraints of the robot arm. Each joint on a robot has a limited range of motion, like your elbow can only bend so far. Additionally, the lengths of the robot's links, its segments, define its overall reach. If a target is too far away, too close, or requires an angle that exceeds any joint's maximum or minimum limit, the inverse kinematics computation will yield no real solution. Another critical factor is called a singularity, a specific configuration where the robot loses one or more degrees of freedom, effectively making it temporarily unable to move in certain directions even if the target is technically within reach. To identify or predict these unsolvable situations, a robotics engineer often starts by analyzing the robot's workspace. This is the entire volume of space that the robot's end-effector can possibly reach. Keeping the target pose within this defined workspace is the first step. Furthermore, checking for joint limit violations during path planning is crucial. If a calculated joint angle exceeds its physical limits, it is an immediate indicator of an unreachable pose. Recognizing singularity conditions, typically done through Jacobian analysis, allows systems to anticipate and avoid configurations where the robot loses dexterity and control. Understanding these limitations is not just about avoiding errors. It is about smarter robot design and more efficient task planning. Knowing about concepts like the manipulator workspace, which is the total achievable area, and differentiating it from the more restricted dexterous workspace, where the robot can achieve any orientation, provides valuable insight. Recognizing the difference between joint space, which refers to the angles of the joints, and operational space, which is the three-dimensional space where the robot moves, helps engineers grasp why some requests are fundamentally impossible. Ultimately, recognizing why an inverse kinematics problem might be unsolvable transforms a potential failure into a design constraint or a Q4 replanning. By internalizing the mechanical boundaries, joint limits, and the unique challenges posed by singularities, you empower yourself to design more robust robot systems, create more realistic task specifications, and develop more intelligent motion planning algorithms that anticipate and gracefully navigate these inherent physical realities.
If you love robotics, like, subscribe, and keep building with us.